So thanks for coming to my talk. It's Nam from the PSC. In this very introductory talk, I will try to briefly introduce what is MPC and why it is useful, and we should put more investigation into use it in real life. So, let's first start off with the motivation, why MPC, what it is used to build. So we can see MPC in from academia to some practical system. Some example including a threshold crypto system. So used to decentralize trust and honesty so that you can prevent a single point of dishonest failure. So suppose you have a system where some nodes are not trusted, or they just simply be compromised. You can also see the concrete example of this in the form of distributed randomness. So to avoid bias, you can also see it in encrypted mempool. So you want a fair transaction ordering, or simply in a threshold signature, so to prevent the whole private key leakage. You can also use a threshold crypto system to prevent honest failure. So just imagine that your private key disappears someday just because your phone is burned. So it is good if you can have some recovery system based off the threshold system. You can also have a more sophisticated form of MPC in the form of programmable privacy. So as Barry tried to give this impression yesterday, you can have anything, just define your circuit and then you can have it. So what exactly is MPC? So MPC stands for Secure Multi-Party Computation. So here we have the M, P, and C, not included secure one, because what is the point of having an MPC if it is not secure, right? So an MPC allows mutually distrustful parties, so they don't have to trust each other for the privacy, but they can still be able to compute a public function F. You can think of MPC as having this small box here, the MPC of function F, that the three parties, Alice, Bob, and Carol, they can input their private input, XA, XB, and XC, and then together they can compute the output Y of the function F on those private inputs. So the security property that we want out of this MPC box include the following. So first of all, of course, privacy. We want that only Alice can know the private input XA, Bob knows XB, and Carol knows XC. So this is a must, the first must. There is also a nice property out of this MPC box that we can have independent of inputs. So XA, XB, and XC, they can be independent from each other. So you can think of the case of salary negotiation, right? So you give a number, your employer give a number, and then you can negotiate. But because you don't have to think, okay, I should have a high number or a low number. You don't have to play this game with your employer because you have this privacy. You can also play the best friend or love game independently from each other. And of course, finally, a must-have property is the correctness. So this box must compute the function F from the private input XA, XB, and XC. So we actually have to think about the security model of the MPC box that we just put up. The first one, which is also the simplest one, is called semi-honest security. So you only have a passive adversary in which you can assume that the attacker will just follow the protocol till the end. And the best thing that it tries to do is to extract your information, your private information during the protocol execution. There is another type of attacker that is more aggressive, active adversary. So you want malicious security out of your protocol, then you have to assume that the attacker can behave arbitrarily, including, for example, sending invalid messages just to screw up the computation, or it can have higher chance to extract some information. For example, if I know that if I give this input and the protocol output something, then this must be your input, then I will just play it, right? Or if I already learned the outcome of the computation and it is not in my favorite manner, then maybe I will just stop the protocol so you will not learn the computation and we will not have any conclusion, so I don't lose anything. There are two types of MPC boxes that we can have. The first one is application specific, and the second one is generic. So application specific, you have seen a lot, right? The MPC of a pre-specified function. For example, here we have the MPC box of threshold signature. So you have a key that is split into KA, KB, and KC, and then you want to sign a message using the whole key K. Then the secret owner of the owner of the secret must participate in this MPC box in the threshold signature protocol in order to produce the signature. Another form of MPC that is more powerful is called generic MPC. You can think of this as the MPC computation of a virtual machine. So you just describe the primitive operation of this virtual machine, and then describe a circuit, a public circuit using this operation, and then you can have genericity. And well, of course, oftenly you are trading off efficiency with genericity. So you have MPC that computes anything, a circuit, but it will not be as efficient as the application-specific one. So we have to make the trade-off here. And then, here I will try to position MPC with the current privacy tool landscapes with those popular primitives that we have learned these days, ZKP and FHE. So when you think of ZKP, right, ZKP allows the prover to convince the verifier that an instant X is true. So, so that is like the prover knows a secret witness W such that the relation of the statement X and W returns 1. So here we can think of ZKP as an application-specific MPC, right? Because we can describe the MPC box of ZKP here. So suppose the prover has the statement X and the secret witness W, and the verifier will input an instance X prime, and then we have this MPC that checks the relation R on X and W, so it must be 1. And then the X and X prime, the input of the prover and the verifier must be the same. And then this bit B is an AND of these two conditions. Then so we have a ZKP of MPC. So in fact, we can also have, there are already like MPC protocol that used to instantiate efficient ZKP for non-algebraic segment like SHA-256. I mean, of course, the verification cost is high, so it is not very useful in the context of blockchain, but it is still there. So it is safe to conclude that ZKP is an efficient application-specific MPC that checks the relation, the condition that we just described. Okay, so what about FHE? So basically, if we think of the simplest form of FHE, it allows addition and multiplication of ciphertext. So it will produce the sum or product of the encrypted values. So to be more precise, here you have FHE stand for a fully homomorphic encryption. You have a ciphertext, CXA, that is the encrypted form of XA. CXB, the ciphertext of encrypted form XB. You can compute using this add algorithm on CXA and CXB, and it will be equivalent to the encrypted form of XA plus XB. And the same for the multiplication. You have the product of XA times XB. So yeah, so like look at this, we can see that FHE can be used to build generic MPC, because you just describe the circuit in this form, and then have a virtual machine run on this this circuit, then you have MPC. But because the FHE operation is very expensive right now, we cannot really use it to compute arbitrary MPC. Of course, FHE also have some advantages compared with the current technology, but maybe we have no time to go over it here. So finally, I want to show this picture of the website here from CS Berkeley. You can see that most of the deployed application of MPC right now, 90% of them are wallets, right? And then the rest are application-specific MPC. So for example, the order book matching by JP Morgan, or some statistic application like intersection, aggregation, mean, medium, etc. But they are all, done by the corporate. So this story of how the user is not the client and so on. So maybe this is not what everybody wants. So how about individual privacy? What if we just want to communicate with another party that is, we don't want to go through the corporate? This is like a call to action. Let's try to make MPC more accessible. And we will show what we are doing in this workshop from 12 to 13 on room B+C. I will also show how to use the MPC protocol like Gabo circuit to build a private Tinder matching. Okay, yeah, that's all. Thanks.
Thank you very much, Nam. We have time for 1 or 2 questions. So, does anyone want to jump in? If not, I will. I have a question that basically while I was reviewing the talk, I thought in SNARKs, until we didn't have Growth 16, which was like the first programmable cryptographic tool that actually existed, the field was like, we know there was potential, but we couldn't squeeze it yet, right? What do you think is the historic moment that needs to happen such that MPC goes from, yeah, we know we can do cool things, but it's yet super expensive and all that stuff, to actually, let's start building all our stuff with MPC?
So I think that maybe there is no jumping moment, because we have constant progression in the development of MPC. So every 2 or 3 years, you have this cool thing that maybe we reduce the communication cost by 2 times, and then we move from 2 times to you move from let's say that 2 megabytes to 1.5 megabytes, and that is already an incredible improvement, because you can think of, if it is just the communication cost of one circuit, one gate in the circuit, then if we are computing billion gates, then it is already something that is incredible. Yeah, so in my talk, I will also go over those improvements quickly.
Thank you very much, Nam. Let's give Nam a big round of applause and thank him.
Thank you.